Alright, let's try this again. My apologies, everyone. I say everyone, whoever watches. Okay, right, so where were we? We were reading this, and I just set up a new function, and I included my imports, and I'm going to get the device for training, but I already have this method up here that says is CUDA available? CUDA is available, else CPU. Considering I've already got that, let's just use it. So set CUDA state is going to be called, I think I have to do, is it self dot? Or this dot maybe? Self dot, alright, cool. So that's that. And then if I go to my main, I'll just comment this one out and then run that. Okay, cool. Nice and simple. I guess let's run it, just make sure we're in line with the documentation. CUDA is available, great. And why does it come out twice, I wonder? Set CUDA state, that's because I'm already doing it up here. Okay, that's why. Because setup calls it. Okay. Well, I tell you what, let's just get rid of that as well. I don't think it's that important. And what's the okay? Oh, Shift F10. Yes. Okay. Cool. Great. So whilst I'm here, let me just check I can hear myself. Hello, hello, hello. Yes, I can. Great. Cool. So define the class. We define our neural network by subclassing module and initialize the neural network layers in it. Every module subclass implements the operations on input data in the forward method. That makes sense. So here's a subclass of module. In the initialization, we're passing we're calling the module's initialization. We're declaring flatten equal to the result of flatten, whatever that is. I should probably know that by now. The regression linear something stack equal to sequential. What was this one again? Is it really, what does it stand for again? Rectified linear unit. Okay, cool. Linear rectified linear unit. Okay. So this is the setup. And what is sequential? Okay, it's gonna tell me after, I guess. And then on the forward, it says and initialize neural network layers in every module subclass implements the operations on input data in the forward method. So let's just grab this, see what comes out of it. Clearly I don't really need to run that anyway. Oh, can I do classes in classes? Not so sure about that. Maybe I can. That's interesting. I don't really know Python that much. I'm just trying my best here. Let's give it a try though. See if that runs. It does. Cool. So if I do neural network, what's going to happen there? If I debug this, do I go inside? I do. Okay, that's great. Step over. Where are you? There you are. Awesome. Okay. Continue. Right. So it says we create an instance of neural network and move it to the device and print its structure. So the device is actually a string. Model is nothing. Model equals network to device. Okay, I see. So does this return my device? No, it does not. Let me do that. It returns a string. Oh, can you probably can't see this. I'll try and zoom in a bit. So yeah, what I'm doing is I'm going to return return if is CUDA available. If is CUDA available, then I don't know how to do ternary operator in. So look, ternary operator in Python. If else, so yes, it was added. First condition is evaluated, then exactly one of either A or B is evaluated and returned based on the Boolean value of condition. If condition evaluates to true, then A is evaluated. Okay. So it would be I want CUDA if that else CPU. So that'll do that now. And in fact, if I were to print the result of this, device equals, and that's going to be a string. Like so. We should get it output twice. Okay, no, we should get it out. That's correct, yeah. Good stuff. Alright. So the device gets passed in to the instantiation of this, and then we print the model that comes out. Makes sense? Let's go for it. Okay, and the neural network is output there. Great. To use the model, we pass it the input data. This executes the models forward along with some background operations. Do not call model.forward directly. See, that's a problem with Python, is that they're publicly available. That's so funny. That is so funny. We pass it the input data. So where does it take the input data? Does it have a... Calling the model on the input returns a 10-dimensional tensor with raw predicted values for each class. We get the prediction probabilities, by passing it through an instance of the softmax module. So model is the output, so I'm going to pass it a value. It's a random. Is it a tensor? I can't remember now. Torch.rand. Let's just output this. I can't remember what that actually does. Yeah, that's a tensor. So it's a tensor of 12828. Damn it! Wish I'd remembered this. PyTorch torch.rand. Torch.rand returns a tensor filled with random numbers from a uniform distribution on the interval. Does this have a type ahead? Let's see, Control B. So it says the size. That can't be right. Let me try that again. Returns a tensor filled with random numbers. Parameters. Size. A sequence of integers defining the shape of the output tensor. It can be a variable number of arguments or a collection like a list or tuple. So how is that 1? So it's a 1, 1, 2, 3, 4, 5, 10, 15, 20, 25, 26, 27, 28. Okay. And then this is 28 times. Possible. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, you know what I'm doing. What am I doing? Let's just do it nice and quick. Yeah, okay. So it's 2 by 2, and what's the 1? What does this do? That is an array of 2 and an array of 2, and this is an array of 2. So it's a 2 by 2 twice. I see. Okay, fine, that makes sense. So let me try and figure that out. That is a sequence of integers. Integer can be a variable number of arguments. Example 4 will give me 4. 2, 3 will give me 2, 3. Okay, whatever. So in this case, it's going to be 1, 28, 28. And then we're going to pass the model x. Model x. And then prediction probability equals this softmax thing, and logits is the result of that. So log integers, maybe, and then y prediction equals the prediction probability of the argmax1. Prediction probability is the result of that. I see. And then this is, okay, I see. Let's give that a try. Predicted class tensor 1 device CUDA 0. So it says it should be 6. Tensor 6. X. Model X. Dimension equals 1. Softmax. So what's this NN softmax? Applies a softmax function to an n-dimensional input tensor, rescaling them so that the elements of the n-dimensional output tensor lie in the range 0, 1 and sum to 1. Softmax is defined as softmax for x in iteration equals some expression on that iteration divided by the sum of j. Was this exponential? Probably exponential. When the input tensor is a sparse tensor, then the unspecified values are treated as infinity, negative infinity. Shape. Input where star means any number of additional dimensions and output is star, same shape as the input. Returns a tensor of the same dimension and shape as the input with values in the range 0, 1. Oi, oi, oi. Okay, wow. That looks important. This module doesn't work directly with NLL loss, which expects the log to be computed between the softmax and itself. Okay, wow. Math stuff. Model layers. Let's break down the layers in the fashion this model. To illustrate it, we will take a simple mini batch of 3 images of size 28 by 28 and see what happens to it as we pass it through the network. Okay. Input image equals randomized tensor, and then we're going to output the size. get rid of that for a second. Torch size 32828. Let's break down the, to illustrate it, we will take a simple mini batch of 3 images of size 28 by 28 and see what happens to it as we pass it through the network. We initialize the flatten layer to convert each 2D 28 by 28 image into a contiguous array of 784 pixel values. The mini batch dimension at dim equals 0 is maintained. We initialize the flatten layer to convert each 2D 28 by 28 image into a continuous array of 784 pixel values. The mini batch dimension at dimension equals 0 is maintained. I'm not sure if I'm supposed to know what that means. Let's go with the flow. Inside a knowledge alert. So I'm so sorry. I'm very bad at maths, but I'm guessing 28 by 28 is that number. Yeah. I wonder where the 3 goes. Okay, I see it comes out. Cool, okay, that makes sense. Linear. The linear layer is a module that applies a linear transformation on the input using its stored weights and biases. Let's try that. One sec. Wow, cool. Okay. Hayfever.com. So layer 1 equals linear, in features 28 by 28, out features 20. It's a module that applies a linear transformation on the input using its stored weights and biases. Hidden 1 equals layer 1, flat image. What's the input size come out? That's 320. I wonder how it's compressed that. There's a lot of math nuance here. I need to understand this all, I think. Okay. This is rectified linear unit. Now I remember it. Non-linear activations are what create the complex mappings between the model's inputs and outputs. They are applied after linear transformations to introduce non-linearity, helping neural networks learn a wide variety of phenomena. In this model, we use rectified linear units because between our linear layers, but there's other activations to introduce non-linearity in your model. Let's try that. Before and after. See what happens. Before, and then after. What was that again? ReLU hidden. I'm not sure what's being told here. Non-linear activations are what create the complex mappings between the model's inputs and outputs. They are applied after linear transformations to introduce non-linearity. They are applied after linear transformations to introduce non-linearity. So they are making curvy lines from straight lines. Is that how I understand that? Helping neural networks learn a wide variety of phenomena. In this model, we use the ReLU between our linear layers, but there's other activations to introduce non-linearity in your model. Hidden one is outputting some differences here. And then when you've run it and then passed it the output of that, I don't know, I don't quite understand this yet. It'll come, we'll get it. Sequential. Sequential is an ordered container of modules. The data is passed through all the modules in the same order as defined. You can use sequential containers to put together a quick network like sequential modules. It says you can use sequential containers to put together a quick network like sequential modules. Okay, let's try that. Sequential modules equals sequential flatten is this flattened thing up here. Layer 1 is that. Linear is that, and linear is that. Now the input image is a randomized tensor, and logits equals that. So the last linear layer of the neural network returns logits, raw values in minus infinity to infinity, which are passed to the softmax module. The logits are scaled to values 0 to 1, representing the model's predicted probabilities for each class. Dimension parameter indicates the dimension along which the values must sum to 1. Let's try it, let's see what happens. Still no output, so I'll continue. Model parameters. Many layers inside a neural network are parameterized, i.e. have associated weights and biases that are optimized during training. Subclassing module automatically tracks all fields defined inside your model object and makes all parameters accessible using your model's parameters or named parameters methods. Many layers inside a neural network are parameterized, i.e. have associated weights and biases that are optimized during training. Subclassing module automatically tracks all fields defined inside your model object and makes all parameters accessible using your model's parameters or name parameters methods. I'm going to have to read it one more time. Many layers inside a neural network are parameterized, i.e. have associated weights and biases that are optimized during training. Okay. Subclassing module automatically tracks all fields defined inside your model object and makes all parameters accessible using your model's parameters or name parameters methods. In this example, we iterate over each parameter and print its size and a preview of its values. Okay. So it's looping over these name parameters and just outputting them. Let's see what happens. In fact, let me just knock off all these other prints because they are now noise. Did that even listen to me then? Let me try that one more time. Model structure. Okay, so it's actually doing tracks all fields defined in such a model object. So I guess all of these manipulations are being tracked here. Because if I look for after tensor 0.22670300, I don't know. Fine, whatever. Let's just continue. Let's see if some of this comes together. AutoGrad, automatic differentiation with Torch AutoGrad. When training neural networks, the most frequently used algorithm is backpropagation. In this algorithm, parameters, model weights, are adjusted according to the gradient of the loss function with respect to the given parameter. To compute those gradients, PyTorch has a built-in differentiation engine called AutoGrad. It supports automatic computation of gradient for any computational graph. Consider the simplest one-layer neural network with input x, parameters w and b, and some loss function. It can be defined in PyTorch in the following manner. So what are we on now? We're on AutoGrad. Okay, let me do that then. Oops. We go run that. So we've got the input tensor is full of ones. So if we were to print that out, x, shift F10, ones. Then we've got 3 zeros. Then we got 5 sets of 3. And we've got just neaten this up a bit. X, Y, W. So B will be a random set of 3. Requires gradient. That's going to be interesting to see. And then the Z or the Z is a matrix multiplication of X and W together plus B. And the loss function looks like this. Let's see what we got. I wonder if can I do to string maybe? I don't know. No. If I just go back one, how do we output this stuff again? Print the model. Yeah, I keep forgetting we can do that. Firstly, because it makes these pretty neat. Bit of learning Python, AI and biology here. Gosh. Let's just do this for fun. Like a good bit of tidy up anyway. I'm just kind of hoping that this automatically formats it for me, but you you probably already know it's not going to happen. Oh, it does. So that's interesting. I suppose it just so let me just undo that for this. And I'm guessing that a simple string like that will solve that problem. Yeah, so okay, so forces it through into string. That makes sense. Good, glad we checked. Nice. Let's do Z. Then we've got a loss. Let's just study what comes out now. So loss is the output of binary cross entropy with logits. Cross entropy with logits. Cross product maybe. tensor 6 device equals CUDA. Oh, ha! This one here. Tensors, functions, and computational graph. This code defines the following computational graph. In this network, W and B are parameters which we need to optimize. Thus, we need to be able to compare the gradients of loss. Thus, we need to be able to compute the gradients of loss function with respect to those variables. In order to do that, we set the requires grad property of those tensors. So what happens if I do false then? What happens there? I don't quite see the difference here. So we've got no difference. Oh, wait, is that that's the false? Requires gradient true. A function that we apply to tensors to construct. A function that we apply to tensors to construct a computational graph is in fact an object of class function. This object knows how to compute the function in the forward direction and also how to compute its derivative during the backward propagation step. A reference to the backward propagation function is stored in grad fn property of a tensor. You can find more information of the function in the documentation. Let's check what these come out as. I know it says it. I like to have a little bit of a documentation on my own part though. Gradient function for z is equal to the add backward 0 object and binary cross entry function for loss. This is going way over my head. Computing gradients. And this is a pretty long article here. To optimize To optimize weights of parameters in the neural network, we need to compute the derivatives of our loss function with respect to parameters. Namely, we need alpha loss. Is that delta? Oh God. Well, it doesn't matter, I know, but I'm also rather interested because of Greek, so alpha letter in Greek. Let's see, all Greek letters. I'm just interested, that's all. Here we go, this looks good. It is the... what have we got here? I guess it's a delta. Could be a delta. Could be a delta. You know, I might have to buy this. This is kind of cool. Yeah, I guess that's what it is. Okay, fine, whatever. Maybe it's just some weird death no one knows. So, okay, reading back. To optimize weights of parameters in the neural network, we need to compute the derivatives of our loss function with respect to parameters. Namely, we need loss over W and loss over B under some fixed values of X and Y. So we're computing the slope of our loss function with respect to parameters. Namely, we need loss over W, loss over B under some fixed values of X and Y. Yep. To compute those derivatives, we call loss.backwards and then retrieve the values from w.grad and b.grad. Loss.backward. Okay. Okay. I'm not sure I understand that. Let's keep going with the flow. I feel like I need to just get through this and then I can start to focus in on some of the details. We can only obtain the grad properties for the leaf nodes of the computational graph, which requires grad property set to true. For all other nodes in our graph, gradients will not be available. We can only perform gradient calculations using backwards once on a given graph, for performance reasons. If we need to do several backward calls on the same graph, we need to pass retain graph equal true to the backward call. Okay. Disabling gradient tracking. By default, all tensors with requires grad equals true are tracking their computational history and support gradient computation. However, there are some cases when we do not need to do that. For example, when we have trained a model and just want to apply it to some input data, i.e., we only want to do forward computations through the network. We can stop tracking computations by surrounding our computation code with torch.nograd block. So matrix multiplication of x and w plus b requires grad and no grad. And let's just get it first. In here, let's comment out this ball. Get rid of all the ball. And that's because Z matrix multiplication, does that require gradient true with torch no grad? Oh, I see, okay. Huh, that's a nice keyword, I like that. That's cool, I like that very much. Another way to achieve the same result is to use the detach method on the tensor. Okay, let's see what we got going here. So we're doing this again. We're detaching and then we're checking if it's requiring the grad. Okay. There are reasons you might want to disable gradient tracking. To mark some parameters in your neural network at frozen parameters. This is a very common scenario for fine-tuning a pre-trained network. To speed up computations when you are only doing forward pass, because computations on tensors that do not track gradients would be more efficient. More on computational graphs. Conceptually, AutoGrad keeps a record of data and all executed operations, along with the resulting new tensors, in a directed acyclic graph without cycle graph. DAG. You like DAGs. Consisting of function objects. Let me read that again. Conceptually, AutoGrad keeps a record of data and all executed operations in a directed acyclic graph. Yeah, okay. Cycle graph. Consisting of function objects. So look at that again. I don't think I looked at this actually. Records operation history and defines formulas for differentiating operations. Okay. In this directed acyclic graph, leaves are the input tensors, roots are the output tensors. By tracing this graph from roots to leaves, you can automatically compute the gradients using the chain rule. That makes sense. In a forward pass, AutoGrad does two things simultaneously. Run the requested operation to compute a resulting tensor. Maintain the operation's gradient function in the DAG. In a forward pass, AutoGrad does two things simultaneously. Run the requested operation to compute a resulting tensor, maintain the operation's gradient function in the DAG. The backward pass kicks off when backward is called on the DAG route. AutoGrad then computes the gradients from each grad function, accumulates them in the respective tensor's grad attribute, and using the chain rule propagates all the way to the leaf tensors. Okay. Let me read that again. Conceptually, AutoGradient keeps a record of data and all executed operations cool in a directed acyclic graph consisting of function objects, so it keeps track of it. In this graph, leaves are the input tensors, roots are the output tensors. By tracing this graph from roots to leaves, you can automatically compute the gradients using the chain rule. In a forward pass, AutoGradient does two things simultaneously. Run the requested operation to compute a resulting tensor, great. Then maintain the operation's gradient function in the directed acyclic graph. Acyclic? How do you pronounce this? How do you pronounce?
Acyclic.
Cool. The backward pass kicks off when backward is called on the directed acyclic graph route. AutoGradient then computes the gradients from each gradient function, accumulates them in the respective tensor's gradient attribute, using the chain rule propagates all the way to the leaf tensors, root to leaf. Okay, that makes sense. Tags are dynamic in PyTorch. An important thing to note is that the graph is recreated from scratch. After each backward call, AutoGradient starts populating a new graph. This is exactly what allows you to use control flow statements in your model. You can change the shape, size, and operations to every iteration if needed. Optional reading. Tensor gradients and Jacobian products. Okay, cool. In many cases, you have a scalar loss function, and we need to compute the gradient. A scalar loss function. Okay. And we need to compute the gradient with respect to some parameters. However, there are cases where the output function is an arbitrary tensor. In this case, PyTorch allows you to compute so-called Jacobian product and not the actual gradient. I'm going to need that one in my lexicon. In vector calculus, the Jacobian matrix of a vector-valued function in several variables is the matrix of all its first-order partial derivatives. In vector calculus, the Jacobian matrix of a vector-valued function in several variables is the matrix of all its first-order partial derivatives. Okay, fine. So for a vector function of y equals function of the vector x, where the vector x is equal to x1 to xn and y is y to ym, a gradient of y with respect to x is given by Jacobian matrix, where j is equal to the derivative of y over x 1 to 1 to n, and then m. Oh, I see. I see. Okay, I see. N m1 to n mn. Let me just read it one more time. For a vector function, y is equal to f of x, where x is equal to x to n, and y is equal to y to m. X to n and x to n, y to m, 1 to m. Okay, I see. Cool. Instead of computing the Jacobian matrix itself, PyTorch allows you to compute Jacobian product. The product of v super t, v exponent t dot product of j. For a given input vector, v equals v1 to m. This is achieved by calling backward with v as an argument. The size of... This isn't v. What is this? God damn it. Greek bloody letters. I love them really. I just want to know them so I don't look like a jackass. Because v is... avocado would be that one. So this is... E? How to pronounce you in Greek? This is mu. Mu, okay. Is that what that is? Size of... It's not mu, okay. My bad. Let's see, it is nu. I know. Oh, is it epsilon? Oh! Oh, is that what that is? Epsilon, okay. Cool. Now I know. The size of epsilon should be the same as the size of the original tensor, with respect to which we want to compute the product. So instead of computing the Jacobian matrix itself, PyTorch allows you to compute Jacobian product v exponent t product of j for a given input vector. So it's the difference between these two. V is equal to v to vm. This is achieved by calling backwards with v. I keep saying v. Epsilon. This is achieved by calling backwards with epsilon as an argument. The size of epsilon should be the same as the size of the original tensor with respect to which we want to compute the product. So the input equals torch.i. Torch.i 5 output equals input plus 1 power of 2 the output backward one's like put the input in, retain the graph equals true. Right, let's just I'm not zoned in yet, so let me just run this instead. I'm really struggling here. Actually, it's perfect because it's saying this is the time to learn maths properly. We're going to need it for solving some of these more abstract, well, to solve the abstract issue that we're trying to solve, which is to play with biology. So if we want to do simulation stuff, we're going to need to understand this this data-driven sense of manipulating the reality around us kind of thing. So I need to start learning these things properly. I'm really looking forward to it. So please just keep joining me whilst I go through this, because there will be a time when I start to understand it properly, and I will definitely offload all my information to you as and when I can. So let's see. Because if you're like me, like I had the worst math teaching, and I really wanted to do it, and I just had really bad teachers, and it's not their fault, but it's also, it just goes to show they probably didn't understand what they were teaching as well, because a lot of them had no way of communicating the thoughts about it. So yeah, stick with me. I will learn it, and I will pass all my knowledge on to you as and when possible, and I will try it in the most easy to understand way I can. So keep tuned. Right. It just takes me a little while to get through these things because I have to churn them a bit, and then they start to click in my head, and then I can start to build little pictures up and stuff of them. But it takes a little while. Okay, so torch.i. Let's just have a little feel about what this is doing. Torch.i. Torch.i. returns a 2D tensor with ones on the diagonal and zeros elsewhere. Okay. Just like a symmetrical line cutting this matrix up. And then you're doing the backward because of what it's just said, which is essentially doing the Jacobian product for a given. This is achieved by calling backwards with epsilon as an argument. The size of epsilon should be the same as the size of the original tensor with respect to which we want to communicate the product. Okay. So in this case, this is okay. So we're running it just again and again. So it's 4, 8. Let's got a diagonal in there. So, okay, so this is cool. So this is doing exactly what we just read, which is putting this line between in the middle of the matrix, and we can see that there's 4s here. Well, I can see it. I don't know if you can see it. Here we go. There's 4s here, and look, this is what it just tells us to do, or tells us what it's doing. It says returns a 2D tensor, a two-dimensional tensor with ones on the diagonal and zeros elsewhere. Cool, makes sense. And we're getting a 5 depth array tensor. Cool. And then it says the input, we're going to plus 1, so that's why these are 2, because it says diagonal and zeros elsewhere. Ones on the diagonal and zeros elsewhere. So we're going 0, 1, and then we're raising them to the power of 2. So I can't quite tell why that's 2. So if I don't do that, if I just take that out, we've got our zeros, but then we're going to plus 1. I don't know why. 0 plus 1 to the power of 2. Exponents first, so it's whatever this is to the power of 2. How is that coming out as 2? Not sure. And then this one's like torch, one's like returns a tensor filled with the scalar value 1 with the same size as input. Returns a tensor filled with the scalar value 1 with the same size as input. Torch ones like input is equivalent to torch dot ones input dot size d type equals input dot d type layout input. Okay, so basically a time saver. Example, input equals torch dot empty23 ones like, so 2 by 3, and it's just putting ones in with the same thing. So it's putting ones in. So if I do, let me just see this. If I do that, it's not going to be 3. It's going to be 4 because it's 2 to the power of 2. Okay. I'm not sure this is... Okay, so now we need to look at the backwards. So it says torch dot backwards. Computes the gradient of current tensor graph leaves. Computes the gradient. So if I did, let me go to paint. Oh, we've got paint already. Classic paint. So if I took a graph like this, and this was Let me just run this again without the, yeah. I'm just trying to imagine things, it might be wrong, but let's say this is, let's just go to 8. Let's go 8 by 8. So we've got 4, 2, 2, 2, 2. Let's do this by 2 so we can actually output this in our graph. Yep. So it's going to be 4. Oh, help me God. Right. Or boson. Help me boson. So 4 is going to be here, and then 2 is going to be here. And then we've got 2 is about here, and 4 is there. So this is calculating the gradient, so it's going to be, so yeah, it would be negative. Well, I guess it depends on where I'm coming from. The gradient backward, it says derivative, doesn't it? Computes the gradient of current gradient. So it's not the derivative. It's what's a gradient in calculus? Gradient in calculus. Gradient vector. Okay, it's a different thing. All right. The gradient stores all the partial derivative information of a multivariable function. Okay. Ah. That is interesting. Right. Right. We have our answer to what to learn next. Oh look, it's three blue, 1 brown. That's great. Oh. Oh, fascinating. Okay. So I've got some watching to do. Right, fine. I don't know this yet, so that's fine. Let's continue. It's nice to see and play with that a little bit, though. Let's continue to the bottom of this. So notice that when we call backwards for the second time with the same argument, the value of the gradient is different. Actually, before we do this, let me just note this down. Episode 12. Need to learn partial derivatives. It's funny because I didn't get to partial differentiation because I hadn't needed it in physics for the stuff I was learning. This is an excellent way to get into this, so I'm really excited about that. Yoo-hoo! So excited. It's gonna be awesome. And you know what? I wonder if Jen Foxbot has some kind of stuff in there for partial derivatives. I'll ask. I think that'd be awesome if she could run through that because she's awesome at explaining stuff, and obviously 3 blue 1 brown as well. I know that I think we'll see how it goes. Okay, cool. So yeah, let's continue. Notice that when we call backward for the second time with the same argument, the value of the gradient is different. Yes, this happens because when doing backward propagation, PyTorch accumulates the gradients, i.e. the value of computed gradients is added to the gradient property of all leaf nodes of a computational graph. If you want to compute the property of gradients, you need to zero out the gradient property before. In real-life training, an optimizer helps us to do this. Previously, we were calling backward function without parameters. This is essentially equivalent to calling backward torch.tensor1, which is a useful way to compute the gradients in the case of a scalar-valued function, such as loss during neural network training. Okay. Oh wow, this is so sick. This is so sick. Wow, we're close to the end of this creepy, scary information here. I tell you what as well. So we're going to do PyTorch, great, and I'm going to use that because George Hotz says to use it, but I'm interested to look at TensorFlow. I don't know if I have to pay for it or what, but I'm interested to play around with that. So there's a couple of things we've got to get going now. We can start to see a path. We've got to learn our partial differentiation and more about calculus. Number one, we've got to check out TensorFlow and revisit PyTorch again. and see, what's happening with those. And then we've got to try and get this back to biology. So what's our first thing that we're going to try and do? I suppose, like, looking at what data sets we have available to us to have a little bit of a study, biologically speaking. The goal might change throughout this process, but the important part is to keep aiming towards the biological scenario. And yeah, right, so got all that. Okay, so once that's all done, what else can we do? So we've got the we need to go back to learning some of these chemical interactions as well, because if you're going to do stuff biologically speaking, you're going to need to understand how things interact with each other. That takes us onto a bit of physics as well, because the interaction between electrons and protons, all that stuff, there might be some kind of quantum mechanics understanding required. Damn, this is exciting, I have to say. Right, cool. I'm gonna call it a day for now, because we're an hour and 15 minutes or whatever it was, and we'll pick this up another time. So let me just type out what this all was. It was 1. Yeah. 1 is going to be finish PyTorch tutorial or getting started. 2, gonna need to learn partial derivatives. 3, need to learn more calculus, or need to familiarize myself with calculus. That's kind of a cool to the above one. Then we've got to check out TensorFlow. And then, so TensorFlow is the other library that does the same as PyTorch. Number 5 is to try some toy implementations of AI using the frameworks. We've got to revisit chemistry. Yep. And I think that's about it at the moment. So so the path. How do you end this? Okay, cool. The path so far. Can you do that? No, that? Yeah. Can I go backwards? Yes. Okay. The path I need to take so far. Okay, cool. Keep loving learning. Stay safe, please. Don't forget I mentioned the UK is going through a little bit of a tough time with COVID-19 again with a spike. So just be careful, and get the vaccination, get yourself sorted, and see you on the next episode. Bye for now.